Welcome to Organolysis. So welcome to another video of the name reaction series. Now before going to start this video, I have an important announcement, that is I am creating a Facebook page for you where you can get different types of problems, which is expected problems and their solution. So go and check it out and follow that pages. So link is given in the description box. You can check it out from there. Okay, so let's start the video. Now our topic is the Corey-Winter Olefination. Now this is an important name reaction for CSIR-NET and GATE specifically. So and questions also came from this topic in the recent year examination, that is CSIR-NET December 2019. So let's start the video. Now for this reaction you have to know some basic concept. From the basic concept is that this from the name you can easily identify that it is an olefination process. So the two scientists, that is a Corey and the Winter, they first developed this new method to form a stereospecific alkene. That so for this reaction they have started with the diol or any kind of 1,2-diol or 1,2-thiol. So I am written over here as a generalized way, that is X is your maybe your oxygen, maybe your sulfur. So X may be your oxygen, maybe your sulfur. So if the X is your oxygen, then it is the 1,2-diol, and if it is sulfur, then it is 1,2-dithiol. Right, now from this they are using this kind of reagent. Now this reagent is basically called thiocarbonyl diimidazole. In short it is called TCDI. Full name of it is thiocarbonyl diimidazole. Right, so you can see here this is a thiocarbonyl group. You can write in this way, that is C double bond O, this is your carbonyl group. So if this oxygen is replaced by the sulfur, then it is called the thiocarbonyl group, and here you have the two imidazole rings, so that is why it is thiocarbonyl diimidazole. Now from this 1,2-diol or 1,2-dithiol, they are using this one, that is a reagent, and they are getting in this kind of 5-membered ring intermediate, and that is basically called the cyclic 1,2, I'm written over here, cyclic 1,2-dithiocarbonate. Okay, so if this X is equal to oxygen, if the X is equal to oxygen, then it is called cyclic 1,2-dithiocarbonate, and if this X is equal to sulfur, then it is called cyclic 1,2-dithiocarbonate. Right, so if the X is equal to sulfur. Now from this they are using this PO R prime maybe or any kind of alkyl group. So this is basically called the trialkyl phosphide. So this is your trialkyl phosphide. So from that reagent they are getting an alkene, and along with this C double bond X, the X may be your oxygen or sulfur, and here the rest part of this is two are the byproducts from this reaction. Now this is an important reaction, so let's see first the mechanism, how to prepare this intermediate, and then after using this trialkyl phosphide, how can we get the alkene. So let's start the mechanism first. So first of all we are starting with the 1,2-dithiol. Now we can write this in this way, that is your R1, that is your R2, and here we have the 2 OH. Now we are starting with this compound, that is 1,2-diol. So this is your 1,2-diol. Now from here we are using this group, that is the TCDI. Now we can write this group in short way, that is your IMD. Right, in short we can write in this way. So oxygen has a lone pair, so it will directly attack to the carbon, sorry, this is carbon, this is your sulfur, this is your carbon. Right, so this is attacked to the carbon here, thiocarbonyl carbon, and it will get back to the sulfur side. Now from here we are getting this intermediate OH, that is your S minus, and here you have the 2-imidazole. So this S minus can back here, and this one equivalent of imidazole will leave from the system. So from that we are getting this one, that is your carbon double bond sulfur, that is imidazole, and here you have the OH, right? So from now this oxygen has a lone pair of electron, so similarly it will attack over here, it can go and can back, and it will leave from the system in this way. So one more of imidazole will leave from the system. So from here we can get this kind of intermediate, that is this one, right? So this is our major intermediate, and this intermediate is basically called the Ionocarbonate, right? So this is your, if this is your, because we are taking the X as oxygen, so that is what it is called, the 1,2-dithionocarbonate. Now from here to this to getting the alkene by using this trialkyl phosphide. Now this the exact mechanism of this reaction between these two, these two means this 1,2-dithionocarbonate and the trialkyl phosphide, it's unknown, or it's so that's why we have two different aspects of this, or two different possible pathways for this to present this reaction to generate the alkene. So we have to see the both of them. So first of all, the first mechanism which is believed to process is that when we are using this POME whole 3, we are using the R prime. The R prime we are taking as in methyl group. Okay, so we are using this POME 3. So the phosphorus has a lone pair of electron, so this will attack directly to the sulfur center in this way, and it can go over here, right? So from here we are getting an intermediate, that is what it is. This is your negative. Now this phosphorus is now positive, and OMe whole thrice, right? Now this negative charge can directly attack to the phosphorus center, so that they are getting an intermediate like this. In this was here the intermediate, that is okay, so this is your phosphorus and POMe whole 3, right? So we are getting this kind of intermediate. Now one equivalent of POMe 3 directly attack to the sulfur atom, and you are getting another intermediate, that is what it is, POMe 3. So it will attack to the sulfur atom like this. So this can go here, and this bond takes over here like this way. So that is how you can get this an intermediate like this, that is your R1, this is your R2, O minus, here double bond POMe whole 3 like this. Okay, so we are getting this a kind of intermediate. Now this is your ylide. From here we are getting that this bond can go over here, and it can go like this, it can go like this, not this one. Okay, so that from here we are getting this kind of alkene, that is your R2, and along with this one we are getting this POMe whole 3. This is your O minus, this is your this is your not O minus, this is your carbon, this is your double bond oxygen, this is your O minus, and this is your positive phosphorus. It will go over here, and it can leave from the system in this way. So from here we are getting these two, that is C double bond O plus POMe 3 free. Okay, now another mechanism is believed from here, that from this step. So this is your another important step. Now from this step, if this bond leave from the system in this way, so that we can generate a carbenoid over here, that is a carbene So we can, this is another process I am writing over here, R2, this is oxygen, oxygen, this is your sorry, not this bond, this two are carbene. Now another equivalent of POMe3 can attack over this carbene carbon, so this is your carbene. So these two are, a mechanism is believed, that is, one is the Elite process and another is the carbene process. So if this attack over here, so we can get, this is your R2, oxygen, oxygen, double bond, POMe whole 3. Now the last part of this reaction mechanism is quite similar, that is, this bond can go over here, it can go like this, and it can remove from the system like this way. So similarly we can get this, that is your R2, this is your major alkene over here, and the last step is the removal of this group, that is simultaneously you are getting this double bond O and this POMe3 free. Okay, so let's see some key points that you should remember. So this is the overall mechanism for this Corey-Winter olefination. The key point of this reaction is, that is, you should remember from doing this question regarding this Corey-Winter olefination, is that the stereospecificity of this reaction. Now stereospecific synthesis of alkene, or you can say it's a regiospecific, because you can see there is this stereospecific alkene you can get from here. And another thing is that this is elimination. So you can see that is the, if this group, these two groups are, we are taking this is in above the plane, so this OH has to be in above the plane. So if it is in below the plane, then you have to rotate the bond, and you can do the same operation. So this is a important step, that is your cis elimination, that is important to this reaction. So if this OH is in above the plane and if it is below the plane, then this cis elimination will not take place. So another thing is that the stereochemistry of the product or the olefin is only determined by the stereochemistry of the starting alcohol. That is starting alcohol means that is when we are starting with the 1,2-diol. If it is cis or it is in trans, then it will determine that which olefin will take place, either it is cis or trans, that is, or E or Z alkene, right? So this is just some key points that you should remember. Now let's see some examples that are very much important to this Corey-Winter olefination. Is that you can see that this is your TCDI, we can write it in short way, that is TCDI. So this is your reagent and this is your substrate. You can see over here these two OH is given in the below the plane, so they are in same stereochemistry. So we can draw the intermediate in this way. So this is your OAC, this is your OTBS, and you can see this is your oxygen, so carbon and double bond sulfur. Okay, so this is your intermediate. Now when we are using this POMe whole 3, now the similar mechanism is basically followed over here. Now we can do it in such a way that is, this can attack over here, it will go over here. You can follow any of the mechanism, either it is carbene process, either an Elite process, so the product will be the same in both the cases. So mechanism is not much important to do the product. So this is your product, and the alkene formation, it takes place over here and it will leave from the system. So that is what you can get from here, is this one, right? So this is your major product from this reaction. Now let's see another example. So similarly we have this TCDI, and you can see this reagent. Now don't be confused with this reagent. This reagent is basically called 1,3-dimethyl 2-phenyl 1,3-2-diazo phospholidine, right? So this is your overall name of this reagent. Now don't be confused with the reagent. The role of this reagent is equivalent to the POMe3, so they are using that one. So its mechanism of this reaction is similar, and you are getting the alkene in this position just because these two OH is in the syn to each other. So the alkene formation takes place over here, and the rest part is undisturbed. Okay, so this is your OMe, and this is somewhat the rest part of this group. Okay, so this is your major product from this reaction. let's see another example of this reaction is this one, that you can see over here there is a three different OH group. That is, this OH is in the above the plane, these two are in same, that is below the plane. So they are given the same reagent and this OTBSF along with this pyridine, and the third step is second is the POET whole 3. Now you have to know the concept that is this is this diol is in the same side. So these two are in opposite to each other and these two are seen to each other. So the alkene formation takes place over here, and the intermediate is also followed in between these two hydroxyl group. So see, this is your this one and this to the, now the alkene formation is being takes place over here, and you can see that this reagent, that is TMS, OTBS, OTF in presence of pyridine. So if these two are protected by using this reagent, that is TCDI, then the only left OH is here, is this OH. So pyridine takes a proton from here, and this OTBS will attach, TBS group is attached to this oxygen, and OTF will leave from the system. So you can write this OTBS over here, and OTF is your leaving group. So this oxygen along the minus attack over sulfur, and it will leave from the system, and you are getting this OTBS and along with the alkene over here. So this is your major product from this reaction. Now the third step is second part of this reaction is this H2PD. So you know there is a removal of this double bond, that is using H2PD, and CF3CO3H, that's important. So there it is basically used to protect this sulfur oxygen sulfur bond. So that is, this is the CF3CO2H, and the water is given, so it will the acetyl hydrolysis will takes place. So after all you are getting that one, this is your OH, and this is somewhat you get, so this is your OH and this is your OH in below the plane, right? So this is overall product from this reaction. So first step is the removal of this double bond, second reagent used to the removal of this sulfur group, and third step TBS, basically the silicon group, not the sulfur, sorry. So TBS basically a silicon group, so this oxygen silicon bond is cleaved by using this CF3CO2H, and the water is given to hydrolysis of this acetyl. Now next thing is that this one, now if you have this kind of substrate and along with this, so they are not using the imidazole group, they are using two small leaving group, that is the Cl. So it can also serve as a leaving group, so that is why they can use that reagent in presence of CH2Cl and DMAP. So you can see here these two OH is given to you is in syn, but they are opposite to each other, so you should rotate that bond. So if you rotate that bond, you are getting these two OH is in planar or into the same plane, but the one change is here, that is just because this oxygen is in below the plane, and when you rotate the bond, this oxygen is going to in upward position or above the plane. So from that you are getting an intermediate like this one, this OH is in above the plane. Now if you rotate that one, so this OH group which is in above the plane, now it will goes to the below the plane, so you are getting that intermediate. So this part is same because we don't change that bond, we are changing this one, so that is why we are getting that one. Now this is in planar, like in this way, so we are getting that in this kind of intermediate. Now the same thing is using is here, the role of this reagent is equivalent to POME whole 3 or POET whole 3, like that. So it can eliminate of those things, and they are getting this olefin over here. But the question is these two group. Now when we are using these two group, now this two group is in the anti to each other, should be anti to each other, because these two is in trans to each other. So that is why we are getting this kind of intermediate. Now when we are using this below the plane bond, so that means we can write this group, overall group, in planar way, and the same thing we can write these two group in this way, right? So this is all about the product of this reaction. Now the same thing is happening over here. Now when we are using the Cl2C double bond S, so similar reagent that is with this one, and this one, there is a similar reagent of this one. We have these two group, that is these two OH is below the opposite to each other, that is which is above and which is below, and in this case these two OH is in the same side, that is which is both these two OH is in the above the plane. Now the major concern of this reaction is you have to rotate that one, because if you not rotate that one, then you can not do this overall product, that is the alkene formation. So from here you can see that these two group is in the same side, and if these two group are in the same side, then these two OH is in like this way. So if these two OH are in this way, double bond S, and you are getting the alkene from here, and that is your cis, that is your syn, right? So we are getting this one, that is your cis stilbene. So this is called the stilbene. So this is your cis stilbene. Now when we are using these two are in same sides, we have to rotate that one. Now if you rotate that one, then these two group, if it is in up, it has to be in below the plane, because you have to change this group in this way. So this is somewhat we get from here. Now this two is in below the plane, just because here you have the hydrogen. Now if you rotate that one, so you can easily see that this pH group has to be in below the plane. So that is, after the removal of this group, the same reagent is basically used. So we are getting the trans variety or the trans stilbene from here, right? So this is your trans stilbene. Now let's see another example of this Corey-Winter olefination is that. Now from here to here, that is, you can see our alkene, and you can see these two are trans dihydroxylation is being takes place. Now how can you produce the trans hydroxyl group? So if we are using the MCBPA, so there is a epoxide formation will be takes place, either is in above or in the below. It will look like this way, So if it is in below the, it will attack from the upside edge, and this OH will goes to below the plane. So from here to here we can use. So using with MCBPA along with this water, we are getting this trans dihydroxyl product. Now similarly we have this one, along with this same reagent we have POM3, and which we are getting an alkene, but this alkene is in the look like this. This is somewhat we get from here, and this is your E alkene, and we are getting 99% of this E alkene from here to here, and this is E alkene because of this two, just because these two group are in anti to each other, so we are getting this E alkene from here, right? So this is all about the example, and let's see some previous year question that we have. The question says that the question is which is came in CSIR-NET December 2009, very recent examination. They have these two OH, you can see over here, these two OH is in the OH, both are OH in the above the plane, and we have the same reagent, that is TCDI actually. So and along with this POM3, you have to predict both A and B product. Now from this concept we have already seen that these two, if this OH and these two OH is in the above the plane along with different side, we are getting the trans olefin or trans alkene. Similar case is given to you over here. So from above concept we can easily eliminate these two options. So you won't get any cis alkene, we are getting the trans alkene. So your options may be either option A or option B. So you have to predict the product B. Now we can easily see from the option B that this oxygen and sulfur, so we won't get this kind of product, we already get the CO2 when we are using the 1,2-dithiol. Now if we are using 1,2-dithiol, then we are getting this CH2 unit. So and along with this CO2 and this one, so we are getting that one. So option A is your correct answer, and this questions came for maybe 4 marks, right? So that's it. So I think I have covered all those topics related to this Corey-Winter Olefination. If you have any doubt, let me know in the comment section. I will definitely try to answer all those questions, and keep sharing my videos along with your friend circle. And if you haven't subscribed this channel, make sure that you subscribe this channel and press the bell icon to get the earlier notification, right? So that's it for this video, and thank you so much for watching.